Hello, my name is Giovanna and I'll talk about our work named Fully Automated Tool for Consciousness Classification using EEG. First of all, for some background information, let's start with the definition of epilepsy, the motivation for the development of this work. Epilepsy is a neurologic disorder with a high prevalence rate, incident in about 1% of the world population. This disorder is characterized by a persistent predisposition to give rise to epileptic seizures and for its neurobiological, cognitive, psychological, and social consequences. Epilepsy includes a wide range of symptoms arising from altered cerebral functions due to a high number of pathological processes. Epileptic seizure is the clinical or electrographic manifestation due to a temporary and synchronized dysfunction of neural networks caused by cellular malformation or neural cells dysfunctions in inhibitory or excitatory actions. The epileptic seizure occurs when there is an abnormally excessive and transitory electric discharge of neural cells due to ionic currents through cell membranes and can be detected with electroencephalography exam. The electroencephalography, or EEG, is a technique that measures big-scale neural oscillations on the brain based on voltage variations captured by different electrodes, most commonly positioned in the patient's scalp. EEG is useful when investigating and monitoring neurological diseases, and it can also be used to observe consciousness dysfunctions or other disturbs that might affect the brain. The registered electric activity can characterize pathologies based on its wave patterns in amplitude, shape, and frequency, as seen in the image. As mentioned, the EEG can also be used to access consciousness stages. The human alert stage results in the detection of beta waves that varies from 12 to 35 Hz. As the patient relaxes and reduces anxiety, the EEG then detects alpha waves varying from 7 to 12 Hz, followed by the sleepiness stages divided in theta waves from 4 to 8 Hz, and finally delta waves from 0.5 to 4 Hz. We observed the data from the EEG and hypothesized that the wavelet transform, an analysis tool dedicated to attributes that vary over different scales, such as time and frequency, would be a good way to process the EEG data in order to access different consciousness stages. A wavelet is a wave-like oscillation with rapid decay, which enables it to represent data through multiple scales. The continuous wavelet transform covers the time-frequency plane with variable window size. This window can be widened in time, allowing its use in low-frequency phenomena, or also be narrowed, making it suitable for high-frequency phenomena. The algorithm procedures starts with the data collected by the EEG being processed by the algorithm developed using MATLAB. Outlier time points are detected for each of the 19 channels of data obtained by the scalp electrodes. These points are then pondered through the definition of a cutoff ratio and stored in a vector, used for linear regression, so the raw data is correspondingly corrected by it. The algorithm separates the EEG data into two frequency bands through the continuous wavelet transform. The first one is called the awake band, determined by frequencies in the spectrum of 9 to 12 Hz. And the second, the sleep or sleepiness band, correspond to frequencies varying from 4 to 7 Hz. The relation between frequency bands' normalized average magnitude was estimated, which allows the algorithm to define periods indicative of either an awake or sleep stage in epochs defined as 30 seconds. Finally, we compare the obtained results with the clinical hypnograms handled by the neurophysiologist. For validation purposes, an image is given as a result, indicating the concordance between the hypnogram and the algorithm results. We obtain EEG data from 40 subjects with 19 scalp electrodes displaced according to 1020 International System for at least 30 minutes. Record analysis was performed using bandpass and notch filters, 0.5 to 70 Hz and 60 Hz, respectively. The comparison between the algorithm and hypnogram resulted in a sensitivity of 78%, specificity of 91%, and accuracy of 86%. The sensitivity returns the probability of the algorithm to be in equivalence with the awake moments of the hypnogram, known as the true positive rate. The specificity gives the probability of the algorithm to return a rightly assessed sleep moment on the hypnogram, the true negative rate. And the accuracy is the overall probability that the consciousness stages are correctly assessed. In conclusion, the algorithm developed shows good equivalence with the clinical reports. These results encourage the application of the algorithm to fast and automatically evaluate the consciousness stages of patients undergoing EEG exams, providing important information for big data studies. It is interesting to note that even though the tool arranges the periods of exam in a dichotomized way into awakeness or sleep, the resultant temporal series shows non-binary values associated. This provides the notion of progression and transition between stages, which can be further investigated with functional MRI data, allowing the identification of regions with distinct functional activity. The algorithm is currently being used in the study of the brain's functional connectivity, together with functional MRI, in order to assess how different stages of consciousness affects the connectivity, especially in the default mode network. Thank you so much for your attention.